Okay. So today we wanted to talk about twistors, but you have to start somewhere. So we'll start with Dirac spinors in 4 dimensions. So 4-dimensional Minkowski space. And if you want to get to understand Dirac spinors, we first need to understand what it is that happens to the algebra of the Poincaré group. So the Poincaré transformations are basically Lorentz transformations with the semi-direct product taken with the translations. Those words just mean the following expression of how the coordinates transform. So you have the Lorentz transformations that act on the coordinates like rotations would in just space. And then you have the translations that shift the coordinates. So the particular structure of this group is a semi-direct product. And well, we have SO31 plus, which means the proper orthogonal Lorentz group. So we're focusing on Lorentz transformations that are continuously connected to the identity. And that means that we can talk about the algebra of Lorentz transformations. So we have the Lie group, which is kind of a manifold, right? And then the Lie algebra is a tangent space at the identity. So you want to be able to talk about the tangent space. And you want to talk about generators. So you want to talk about the group being generated by transformations near the identity that you kind of like integrate up. So that's why we restrict our attention to this piece. And then we have the semi-direct product. I just need to remember the symbol on LaTeX for that. But that'll just be a minute. For now, we could just say times so this isn't just the product, it's supposed to be the semi-direct product. So I'll put an S here. This is not the standard notation, it's just that I don't remember how the symbol looks like on LaTeX. But that's the group. That's the group that we're interested in. And what we want to do with this is first understand what the algebra of these transformations looks like, right? So we call E the elements, the momenta, the generators of translation, right? So these are just vectors in Minkowski space. And we have the Lorentz transformations. Sorry, this is all just a mess. And they satisfy an algebra, right? So what do you think translations do? If I take the commutator between two translations, what would I get?
You basically get 0, right? They commute.
Very good, yeah. So translations commute. And this is like a feature of the space being flat, right? That if I just went here and here, it's the same as going here and here. It doesn't really matter. Well, maybe I put those fingers, I put my fingers in the wrong places there, but that's what translations do. Now, the non-trivial group structure comes from the rotation parts or the Lorentz transformation part, right? So the Lorentz transformations now involve boosts and rotations. And let's see.
Okay, just to clarify again, like M is the set of Poincaré transformations and P mu is just the momentum, right?
No. So both are elements of the group of Poincaré transformations, P and M. M is are the elements of the Lorentz group, whereas the P are the translations. So eta here is the metric on Minkowski space, and Lorentz transformations are basically those which preserve eta. What does that mean? I take
gives you eta.
Yeah, very good. This is what we want from our Lorentz transformations. I apologize for the mix-up of the font sizes. It's just that some of these are screenshots and some of these are what I'm typing. So this is the group of Poincaré transformations. Now, if you wanted to explicitly see what these M's could look like, then let's say we're considering the action of M on a vector, a 4 vector.
I think your audio.
Am I back?
Yeah, you're back.
Yes.
Yeah, sorry about that. I have to be very careful about the cord that connects my microphone to my laptop, it seems. Okay. So now this is what it looks like if you wanted to understand the matrix elements of M acting on some vector. And I'll leave it to you to figure out why we have this many indices. But yeah, that's what you usually mean when you say you have a matrix representation.
Yeah.
Cool. Now, spinors are weird objects that transform still under the same group. Like they're still representations of the Lorentz group, right? So vectors are. So let's go back to a discussion we had a few episodes ago about what it means for something to be a vector in the first place, right? Is vector with respect to something, right?
Right.
So the Higgs field, as we discussed, is space-time scalar, but it's actually a pair of space-time scalars. It's a vector with respect to internal SU2 transformations, SU2 left transformations.
Right.
So it's in the fundamental representation of internal SU2. So it's a doublet, if you call it that. So it has these two complex components, and then as far as the internal rotations are concerned, it really acts like a vector on that space. Now these are vectors. So 4 vectors are vectors with respect to the Lorentz group. So under Lorentz transformation, basically you have this property. They're sort of rotated and boosted the way you want a vector to be. So they're not invariant, right? They're covariant.
Right.
Scalars are what are invariant.
Right.
Now, spinors aren't vectors, right? They don't have these indices. Let's put it that way.
Yeah.
Spinors come from a further observation. Let's do this. Towards Weyl spinors. So I'll start by describing what Weyl spinors are, and then we can move on to the Dirac spinors. So Weyl spinors, you would discover them if you realize that at the level of Lie algebra, you have the following fun fact. Yeah. So basically, you can, in words, this means that you can split up every element of SO31 to product of elements of SU2. It's as though you have twice as many SU2 elements I will give you.
Right.
Hello.
Yeah.
I apologize for that. I understand that it's very exasperating. Anyway, you could say, well, how would you split up generators this way, right?
Hmm.
And the answer to that is the following. So first, let's try to separate rotations and boosts.
Okay.
So I'll call rotations.
So here, would
GI?
one of the SU2s correspond to the boosts and one SU2 to the rotations?
No.
That how
So
it works?
it's a bit more subtle than that, but
Involved.
you're
Okay.
close.
Okay.
You're very close. So let's rewrite the Lorentz algebra. So what's the Lorentz algebra? The last line here, right? In terms of these two, right? In terms of these rotations and these boosts. So first, I have to tell you what they are, right?
Right.
And they look like this. So I take the 0i elements, those are the boosts, and then, oh, this looks cut off. I'm sorry, I can get you a better screenshot. Well, but you can see that this is a half, right?
Yeah. Should be fine.
So that's how you isolate the rotations. I, j, and k are all spatial indices. So I split the space-time index mu into 0 and ijk.
Right.
So if I pick the purely spatial elements and then I dualize them, I get the rotations. And then I take the 0i, the mixed element, that's going to give me a boost. Notice that both of these are spatial vectors, right? The I runs from 1, 2, and 3. There's just 3 of each of these. If any of this is going fast, you've got to stop me. I'm more than happy to spend more time on it. Because it's important for us to absorb this in order to really see what happens later. So now these satisfy the following algebra, right? So it's almost like saying that the rotations consist of one SU2 and the boost consists of another SU2, but there's some mixing term here,
right,
between J and K. So then you want to separate these, like you want to really pull this apart into two SU2s. Again, for reference, the SU2 algebra is this one. Ji, J is I epsilon, ijk, jk. That's just, so the structure constants of the Lie algebra are just this epsilon ijk, the completely antisymmetric tensor in 3 dimensions. So I repeat so the rules are, I repeat any two indices, it vanishes. And then if I exchange any two indices, the sign changes. Those are the rules of this object.
Right.
So what I do now is I identify the following combinations. See, another annoying feature is that the K satisfy this thing with a minus. It's not quite what we want from our SU2. So let's see if I can.
Wait, yeah. So just to get the physical intuition right, like the boosts we are talking about are they like some sort of curved trajectories or something like that also count as part of?
So I'm sorry, we should have started with that. So you learn this formula for Lorentz transformations where you go like, what is it? There's like an x minus vt over square root of 1 minus v squared over c squared, the gamma factor, all this kind of stuff. What are those transformations? Well, those are the boosts. So let's start. If you you could set aside relativity for a second. I mean, you could set aside special relativity. You could talk about this purely in terms of Galilean relativity, right? So a basic boost in Galilean relativity is how you shift between reference frames of different velocities.
Yeah.
So x.
Okay.
X equals x the other minus vt or something like that. That's a boost transformation.
So
and then
okay. The question was when like you mix J and K, right? What exactly is the mixing like? Is it like you're just having some sort of like acceleration or something like that, and is
No,
accounting for that, or is it like something very vague or something like that?
no. So you aren't talking about acceleration yet. It's just so the mixing between J and K is kind of like saying what happens if so. Now a boost basically means that I have one reference frame moving in some constant velocity. So just to go back to my previous discussion,
Yeah.
how you transform between coordinates of reference frames at different velocities, right? That's what boost transformations are.
Yeah.
Since velocity is involved, they're kind of a mixing between the space and the time part of the Lorentz transformations. That's why it's 0I.
Right.
Okay.
Right? So then what you want to do is say, what happens if I both consider these, I both consider a rotation, right? And what one of these particles say is moving at a different velocity. One of these reference frames is moving at a different velocity than the other. Right. So how do I compose those transformations? So like I do it in one way or do it the other way, and then in the end is just another boost that relates those two pictures.
Okay.
So that's what the boost transformations are. So it's good that we kind of get an intuition for that. Now you can write things in terms of what's called the rapidity, and the rapidity is basically V over C. So it's like some function applied to V over C, but let me just get my conventions
The
right.
hyperbolic sines and cos.
Exactly. So
Yeah.
those transformations that you have, right, they just become hyperbolic cos and sine transformations. And in particular, it means that you can write these matrices like rotation matrices. So normally rotation matrices would be like cos, sine, minus sine, cos, right? But now you'll have hyperbolic, all of these, essentially the same. Instead of sine, you have sine hyperbolic. And the angles are not angles. They're really these rapidity parameters. It's like V over C. So now you can much more concretely talk about what this could mean, right? What this could mean is just you take a commutator between these matrices with an angle and a rapidity factor, like a boost factor, and then you just work out the difference, and that'll be some funny boost. So that's basically what you're doing. Cool. So now we form A and B, which are just this complex combination of J and K. It's good because SU2 consists of 2x2 matrices with complex entries that satisfy determinant equals 1. Right. So, but then you can also write SU2 in terms of SO3. So that's why we have this these three-dimensional vectors instead. And they satisfy just two copies of the SU2 algebra, and they commute with each other, as in they commute with A and B commute. So I'll just put down the algebra here. Sorry about that. And as you can see, we have this last commutator.
Right.
So that's really nice.
So that's some sort of symmetry in the mixing of like J and K, right? Because A and B are like there's some sort of complex conjugation happening over there. Yeah, that's essentially okay.
Yeah, that's basically, so you just plug these identifications in, and then you just work out the algebra, and you'll find that it sort of straightforwardly becomes these things. And under parity transformation, sorry, that was not supposed to come out that way. Typesetting is a bit of a nightmare when you have this system. But wrong. Anyway, this is the parity transformation.
Got it.
it takes a mirror image of your spatial vectors, and then it leaves the zero component alone. Right. So that's what you would normally imagine when you were talking about chirality in space. Right. Under the parity transformation, what happens is that the rotations are still rotations. Because, I mean, this is something that you could work out, but rotations will just be the same.
Yeah.
But boosts will change sign, because it's like x plus vt or x minus vt, or minus of x minus vt, right? Depending on whether you do a parity transformation or not.
Yeah.
So basically, what happens is that J will go to J, but K
go to minus.
Exactly.
Yeah.
So this is what happens. And this ultimately means that A exchanges with B.
Right.
So the point of noting this is that under parity, you could basically see that these two SU2s are kind of like chiral halves, right? There's some sense in which they exchange under parity.
Right.
For a given parity, they're just like, you can really think of them as a left-handed and right-handed rotation transformations in a way. So
I have a question.
Yes, please.
So two things. If we go back to the J's and the K's that we decided were the boosts and the rotations, because they belong to SO13. Okay, forget with them belonging to SO13. But so the J's basically form a rotation subgroup embedded within the thing.
Yeah.
Right. So, and we can choose rotations to be something that are generated by matrices that are purely real. Boosts also we can generate by things that are real, that are like inherently just purely real.
Yeah.
So the J's and K's are we choosing them to both be real here?
Yeah. Yeah.
All right. Okay. Then if you go down, like you said that J, like under parity, J, the boosts stay the same, but no, sorry, the rotations stay the same, but the boost flip sign.
Yeah.
So will that? So say we just consider the boost, and we took like eigenvectors of the boost, right? Then would the eigenvectors of the boost also change the same way? Like would they be that is for pseudo vectors, right? So would the eigenvectors for boost be pseudo vectors?
Let me think about what exactly those mean. The eigenvectors of the boost transformations. Okay, so you find some representation.
Wait, so what was your question again? So
I guess what he's asking is, no, I think that that is the case. So you can really think of these KIs as eigenvectors of some boost operator. So if you wanted to represent this on some, like if you wanted to think about it as an as an eigenvalue problem in a quantum theory, which is not what we're doing yet, but if you wanted to do that, or you just wanted to, so basically giving the algebra a representation is much akin to just picking, like solving the eigenvalue problem, so to speak.
Right.
Because these k's are now concretely some vectors. I can write them down. So in some kind of eigenvalue problem, you could think of those as the eigenvalues of the boost operator. That would satisfy this algebra. Now this bracket here is just commutator between these matrices. Right. So that's the sense in which you have this happening. Well, I'm not sure if I wanted to say it that way. But okay, well, let's put a flag there and come back if you feel like we can make more sense of it later. So this is just one. Okay, so this is one funny fact about SO31. There's another funny fact, which is that it's related So there's a homeomorphism to SL2C, right? So let's dig into that. So a lot of cool things end up happening in order for us to be able to talk about spinors at the end of the day. Yeah. Sorry, my laptop is being. Yeah. Cool. So to see this, we first need to understand how objects can transform, like what objects transform into SO2C. Right, so SO2C means a special linear group in 2 dimensions with complex coefficients. Right, so SU2 was, as I said, 2 by 2 complex matrices that are unitary and satisfy determinant equals 1. Here, these are they don't have to be unitary. They're just matrices with complex coefficients and have determinant 1. What we start with on the left is objects that essentially are 4 vectors, right? There's 4 real components.
Yeah.
So here's the game to play. You introduce, so you introduce the 4 vector of polymatrices. So what do I mean by that? I mean each component of this vector is the polymatrix.
Okay.
Sorry. Let me see that green thing again. Nope.
1 minus 1, 1, 1, and I minus I, right?
Yeah, well, you want to create a 0th component because you want it to be a 4 vector. Oh, sorry, I just repasted the same thing. Matrices are the worst to sit and type out on LaTeX, so I'm trying to really save us some effort here.
Oh, okay.
So you make the 0th component just the identity,
Right.
So you're right. The 3 are the polymatrices you're familiar with from 1, 2, and 3. But the 0th one is just the identity matrix. Okay. Now, once you're equipped with this, what you can do is form a combination that looks like this. Okay. Okay, well, that was disappointing. Yeah. So I take my 4 vector, x0 to x4, and then I just dot it into this x mu. What do I mean by that? I mean that I take x0 and then it's like x0, 0, 0, x0. That's what it means to say that I'm doing this dot product, because it looks weird. It's like one is 4 matrices and one is 4 numbers. But matrix, you can make sense of a multiplication between a real number and a matrix.
Yeah.
So look at this. This is a 2 by 2 matrix, complex coefficients. And now the funny thing is what happens to the invariance property. So let's put it this way. We know that under Lorentz transformations, the following is invariant. Mu x nu. Right? So you could say that Lorentz transformations leave this alone.
Right.
Yeah.
Right? So this is like
this is just another representation of squeezing the whatever the matrix between 2 lambdas, right? Lambda
exactly. Basically,
yeah.
what I do is that I transform these x twiddles. So basically, I can take lambda, eta, right? And then eta just transforms with different indices, and then it's the same thing. It's the same quantity. But in terms of these components, what is this? Just so that we know what we're talking about. It's x0 squared minus x1 squared minus. Sorry.
X3 squared. Yeah.
Yeah. 3 squared. Yeah, well, there's really just x2 squared, but I was lazy to write it out. So that's the quantity here.
Right.
And the funny thing is that is the same as the determinant of x twiddle. Okay, which is good.
Yeah.
Because under an SL2C mapping, okay, what is an SL2C mapping? An SL2C mapping is the following. Okay, the determinant of n. So what you'll do is if you take the determinant of this, it'll split up into the product of determinant n, determinant x, determinant n dagger.
Right.
Let me write that out. Determinant of n tilde x n dagger is just going to be the product of determinants, right? Going to be the determinant tilde x, determinant of n, determinant n dagger. What's nice about SL2C is that the determinant of any element is going to be 1. That's the S. So that's just determinant tilde x. Oh, too many brackets. Yeah, too many brackets.
Yeah.
Okay.
So it's like a defining property of an element. I mean, an element of SL2C.
Right.
But here's the interesting thing: the map between SL2C and SL13 is 2 to 1. And the reason for that is if I took n equals, oh no, I. Yeah, I want to write identity, right? So if I took either n equals plus or minus I, it would lead to the same, it would correspond to the same Lorentz transformation.
Oh, because, okay. So because you're essentially squaring it, so.
Yeah, exactly. So you see, the thing is that, okay, so let's just remind ourselves of what Pradyot just noticed. This is how vectors transform, right? But tilde x transforms with this other structure.
And then, yeah.
Oh,
wow. And dagger. And dagger, yeah.
Exactly. So in some sense, you have doubly many n's doing the work of one lambda, so to speak. And that's the reason that it's actually double covering it.
Right. Okay.
So in a sense, so now we have these two facts, right? Now what we do is let's ask for, okay, cool. So let's ask for representations of SL2C, right? So we call it, like, you have these vectors, they're all representations of the translation group, whatever, and then they transform under rotations. Who transforms under SL2C? So let's pose the question. Let's do it this way. Who transforms under, let me do math mode.
Okay.
Right? So these are going to be objects that have, okay, so they'll have different indices, right? They're not the same as space-time tensors, and the indices will run between 1 and 2. So we'll start with the fundamental representation. This is just a name, which means something that transforms a vector like under SO2C.
Hmm.
And congratulations, these are your left-handed Weyl Spinors.
Oh, okay.
Weyl.
Yeah.
Okay, now we have the conjugate representation. And as you can imagine, those would be
Phi bar phi dash of alpha is equal to n beta alpha phi of alpha. Yeah.
good guess. It's just that the conjugate representation comes with a different index. So they're dotted.
Right.
Oh, okay.
So you see these are conjugates. So it's n conjugate.
Right.
You have these dots. The dots run from 1 to 2. So those
Wait,
are.
isn't it? Oh, it's just a conjugate. Okay, cool.
Yeah,
cool.
yeah. So you have these dotted and undotted represented, but you see these are right-handed Weyl Spinors. And then what you can do is you can kind of like talk about the raised index representations if you wanted. And we'll talk about who raises indices in a second.
So does the n alpha betas, are they something like a helicity operator here?
No. Let me think. Are they helicities? You could certainly represent helicities in the form of some n. That is true.
Okay,
They're not
so in a certain representation.
They're not necessarily helicity transformations, although they end up like that when you do the Mackay stuff.
Okay.
Yeah, so you see, a helicity transformation is essentially a phase. And what happens is that it really just it just looks like a phase multiplying your spinors, like these left and right-handed spinors. So that's like a particular form of n. And helicities don't form SO2C. Helicity transformations are actually just U1 transformations because they're just a phase, a complex number.
Oh, right. Yeah.
Okay, so that's perhaps one thing about group theory that I don't completely understand. Here we have a spinor, which we're saying is a representation of SL2C.
Yeah.
Okay. Which could also be a representation of SO31 because we just said that SO31 is isomorphic to SL2C.
Yeah.
Homeomorphic. Yeah.
So the thing is that it's homeomorphic, but okay. So there's a story here called so you have to follow Mackay's method or Wigner's little group method to classify the representations. So you see, the thing is that you start. So you want to classify these representations. You start with a Poincaré group, and then let's set aside spinors for a second, and then let's just talk about the Poincaré group. First, what I do is I pick a representation of the translation part. It's very easy to do that. It's some vector. Okay. And then what I do is I ask about all transformations in the other part, the Lorentz part, that leave this vector alone. Right, remember, generically rotations will not preserve a vector, but I could do rotations around an axis, say, and they will certainly preserve a vector. In 4 dimensions, if the vector is time-like, I will form an SO3 group of rotations that can preserve a chosen time-like vector. That is the spin label. That is what becomes spin in quantum mechanics. See, spin is always just a representation of SO3 or SU2.
Right, exactly.
Now, the situation is much more subtle if you have a null vector. If you have a null vector, you actually have a non-trivial structure of the little group. The little group has a rotation part that's SO2, and it has translation part, but you trivialize the translation part. And then you only consider the representations of the SO2 part. So the SO2 rotations that kind of rotate the null vector.
Right.
Which is much like what happens if I just look at my finger in flat space. I just have this SO2 rotation, right? That's the U1. Those U1 labels are the helicities. That's how they sort of come in. So in order to write that, to sort of really get the story down, you first need to understand how to do the Lorentz transformation that takes whatever vector to your representative vector. And then you talk about the labels associated to the ones that leave this vector invariant. So that means that in this story, if I translated everything into SL2C, I would first break up N into a part that takes my spinor to this representative spinor, and then I would have a U1 subgroup acting on that representative spinor that would leave it alone.
Okay.
So that's sort of the way in which this representation theory works. So the thing is that these are just representations of SL2C, whereas the ones that we're discussing, helicity and spin and so on, are unitary irreducible representations. The reason why you care about unitary irreducible representations is because you want to talk about particle states in quantum theory.
Right.
This is just all classical, like we're just talking about objects, right? So it's kind of easy. There's a Weyl spinor or whatever, like we don't really care. But these are not necessarily unitary representations.
So you're basically like projecting the whatever groups you have into a unitary group to get the unitary representation, right?
Not quite. So what you're trying to do is you're trying to find representation. So you're trying to find elements of the unitary group which reproduce the algebra that you're interested in.
Okay.
Yeah, and you want those to be irreducible representations. Right. So you don't want that to be a direct product of something else. Like I don't want to put one, like, if you have some block diagonal matrix, right? I don't want that. I want them to be irreducible. And I call those my particle states. And to get those, I do this trick, like this little group method and all this kind of stuff. I think that Sir shared Wigner's original paper a long time ago on the work. So
he did.
That. Yeah. I mean, we could even go over that one day, because I spent a lot of time thinking about that at some point in my PhD. Because to date, there's no good understanding of why you're throwing away the translation parts of the little group of the massless, of the null vectors. You could say, what happens if I included those? What happens is that you get these continuous spin representations.
Oh, okay.
You don't see them. They don't appear in the standard model. You don't understand why they don't appear. There's no field theory for them. Very understudied. And we were trying to understand these. We were trying to understand these in de Sitter space back when I was it was my first project during my PhD. We didn't get anywhere, but it's still there. It's still very interesting.
I guess we could plan it as a as a topic for some other call. Yeah,
but does that address your concern, Sharon?
Sure.
No, I just need to sit and think about it a little bit more, and then I'll be fine.
Sure. Yeah, no, feel free to write back if you have more questions. Yeah, so then these are just you could say contravariant representations, what I've written down here, or copied down here, right? Just re-raise the index. You could say, okay, what is the thing that raises or lowers indices? And it turns out that it's a pair of these epsilon tensors.
I thought it would have been some form of the ends themselves, but okay.
Some cool thing? No, it's gonna be just these epsilon tensors. Why? Because we can do a very similar exercise to what we did with the metric. Okay, well, no. Why? We already know. We already know why. Because what is determinant x?
Okay.
Epsilon xx, right?
Right.
X total. So that this is the object that's contracting, right? And what you find is, essentially this property.
Okay.
Wait.
Yeah.
Okay. So instead of having some sort of okay. So even the squares have the same sign. So you square the epsilon 1, 2, and then you get back epsilon 2, 1, 2. I mean, you
Squares?
square 1 to transform, 2, 1 to transform into 1, 2. Yeah. So, I mean,
Why would you? You
that's
mean if I
not
took
what
epsilon
usually
A, B,
happens.
epsilon
Right?
B, C?
Yeah.
Oh, yeah. Epsilon is,
It's not like there's an additional constraint happening over there because you're imposing the plus minus 1 condition. You have that kind of like, okay.
Yeah. So basically, in expressions, what I said about them being used to raise or lower indices is just this. Let me put it down here. I'll just put it down. Come on. Yeah, wonderful. So I can use the dotted epsilon to raise or lower, and then I use the undotted epsilon to raise or lower, depending on which spinors I'm talking about. Right. So now you could say, well, remember my x-twiddle trick? What was going on there? Okay, now we have these new indices, right? We understand that there are these new indices that are playing a role. So we could say, well, what was my x-twiddle? Remember, it was a. This. And its transformation is given by what goes on here. Okay, so you'll see some bells and whistles, but we can parse it. So really, the sigma has a dotted and an undotted index. So in many ways, you could say that that a Lorentz transformation comes from a combination of an n with undotted indices and an n with dotted indices.
Right.
Okay, so let's just simplify. Well, what does that look like in terms of sigma? Well, sigma's transformation is the following. So you see, it has a vector index, so it has to transform with the Lorentz. But it also has two spinor indices, so it has to transform with each one of these. Right? And similarly, you can have a so-called sigma bar representation, which I could pull down here. I just raise the indices. So that's basically what happens. You see, when you have a vector index, it's like you can have, since sigma connects vector indices to spinor indices, and since sigma has one dotted and one undotted index, it's kind of like saying every vector index is worth two spinor indices, but with dotted and undotted.
Okay.
Right? So you see, I take x mu, and then I go to x-twiddle, but x-twiddle has dotted and undotted. Okay, so now let me just flash an expression, and so this is just a bit of a bonus, and we can think about its deep implications later. But here, come on, where are you? Yeah. So this is the anti-commutator between two spinors, giving us the momentum, generator of translations.
Oh, wow. Okay.
These are supersymmetry transformations. These are n=1 supersymmetry transformations. So you see, when you say, oh, I can have fermions somehow being related to bosons, this is the key relation. Right. Yeah, one dotted, one undotted.
Oh, okay.
Wait.
So actually, what Alanak's lecture notes are about is supersymmetry, in 4 dimensions. And he does it starting from this group theoretic way, so I recommend it if you want to understand supersymmetry.
Yeah, I think
So
we
now let's
can link
talk
that
about,
as well. Yeah.
yeah, we could do that some other time. Let's talk about generators.
Hmm.
So what's going on here? Well, what we do is we first take our sigmas and form these guys. And you will notice that a very similar exercise can be done for your old school Lorentz generators and with just vector indices. But it's just that,
Hmm.
see if it's gotten updated. Oh, it came. Thanks. So you see, I have just the following antisymmetric combinations of sigmas, and I call them sigma mu nu or sigma bar mu nu. And then these still have two. No, so these have purely undotted or purely dotted indices. That's why I'm doing this, right? So you see, I'm contracting the dots with the dots. I get something that's the undotted with the the dots with the dots. I get something purely undotted, and similarly here. Now, what does this alpha beta mean? Well, we could expand it. It's basically sigma mu beta gamma dot sigma bar nu gamma dot alpha, right? So the dots contract. You just do that. That's what this notation implies. And they will satisfy the Lorentz algebra, right? Remember that for the Lorentz algebra, we needed something that looks like M, right? M has two spacetime indices.
Yeah. Yeah.
And similarly for sigma bar. Okay? But now why were we calling these spinors left-handed and right-handed? We'll see. It's because of how they transform under the Lorentz transformations. So I'm not saying that this is what explains it to you, but okay, so these omega mu nus are just arbitrary parameters. You can think of it as a mixture of an angle and a boost angle, right? So it's like an angle and a rapidity parameter. It forms this omega mu nu. That's where it comes from. But you can ask about their transformations with respect to A and B. Okay, so you have A and B that are spatial vectors, but whatever. I take a sigma, I play this game, I form the sigma mu nu, I do all this complicated exercise. And this is what I find. Right, so you could ask, what was the point of your whole SU2 times SU2 story? That just seemed kind of out of place.
Right.
Right. Well, this was the point.
Okay.
I mean, okay. I don't know. I'm just thinking about like forming a matrix with phi dot x or whatever that is. So yeah, so if you form a matrix with phi dot x tilde, then you have some sort of like a square because they don't exactly cancel out, right? Like, I mean.
Oh, you mean products of spinors?
Yeah, so they don't cancel out, right? Like it looks like they cancel out, but actually I don't suspect they cancel out.
Oh, you mean do products of spinors, are they scalar or are they not? Is that your question?
Yes.
Good question. Okay. So let's think about that. Generically, okay, let's see. So we could have these kinds of products. Okay, so let's just open a new section. So the oh, come on. Weyl Spinors. again, remember, you have to be careful about how these things appear first. Well, okay, that didn't appear at all, so I'm going to have to do it again. Oh, sorry, that was the wrong expression. That was really something going on here. Just give me a second. Whoa, I lost screen sharing. Something happened. You know what, I'll resume in a second. Sorry. Okay. Back. It looks like my laptop is now running on fumes. It's having a very hard time keeping up with these two screens and Zoom. Share screen. Spinors. Share. Cool. So we have, finally, we have these products, right?
Yeah.
And as you can see, they're not quite scalar. They're kind of
They don't cancel.
they're kind of
each other.
Grassmannian.
Yeah.
So okay, let's continue our dive into these, because that's another important feature of these spinor variables. Their sort of Grassmannian nature.
I mean, I noticed like when the ordering of like the x and the action
I and
was
psi.
kind of like not really canceling. Yeah.
Exactly, exactly. So it matters whether you raise one, lower one, or raise the other and lower the other. So you define this psi so that you have the following happening. Sorry.
Okay.
Yeah. So this is what a generic product would normally look like. Right. So now you could say, well, why is this? It's because there's a handedness involved, right? Like, psi and chi bar have different handedness. And we have to be very careful when we talk about how we're combining these representations of SU2. Right? In particular, you have all of this going on. So the Hermitian conjugation, you can flip the handedness. And yeah, so these are what are called Peirce identities. Now, you can generate various representations of the Lorentz group by combining these, right? So you basically see that one of these is like a half comma 0. So I take SU2, SU2. Left-handed means half comma 0. Right-handed is 0 comma half.
Right.
And then you can tensor these representations together. Right? You can take products. That's what a product of these matrices, a product of these spinors just sits in one of those tensor product representations. So, you have, from SU2 representation theory, you have the following fact. So you have these tensor product representations. So half tensor 0, half comma 0 tensor 0 comma half is half and half. Where it kind of makes it's kind of intuitive. You have to use the rules. So generically you're using the following sum rules. So if I have to take a arbitrary representations tensor product with the fundamental representation, then this is what happens. Okay. I say things and then the expressions don't appear. Okay, so you see you have direct sum resulting from a tensor product. Right? And 0 is a trivial representation. And really what you can do is you can actually take, sorry, let me do this again. That was chunk. So I can take a generic half integer spin, or any integer spin, and then write it as a tensor product of the fundamental over and over and over again.
Yeah.
So to some kind of powers. That's what these expressions mean. Sorry for the bad cutting, but you see that this is r, so it's half to the tensor power r, which means I take tensor product of half.
Right.
Similarly with s over 2. And then I use this rule, right? So this thing just follows from this rule, this j over 2.
Yeah.
Right. So here nothing happens, but as you can see, you get something like a bispinor if you do this. About that. Okay. So you see, this is the result of this. It's a half and half, right? So left-handed half and a right-handed half.
Yeah.
Right? But now what we could do is take two lefts and we'll get a vector, sort of left-handed vector if you wanted. Right? So
yeah, that makes sense. Yeah.
Yeah, that's the one I want. Yeah, so where this is coming from is the following combination. So it gets a little intricate. You're basically building representations out of more simple ones by doing this. This is the recombination theory. Well, recoupling theory, whatever. So that's what some people call it. It's related to the addition of angular momenta in quantum mechanics.
Yeah, I can see how.
Yeah. So, do you guys mind if I take a short break? I'll be right back. There's just something I need to take care of. Okay, so let's just pause for a second. Finally. Am I sharing the screen?
Yeah.
Cool.
The Dirac Spinors screen, right?
Yeah. So we're finally going to get to Dirac Spinors.
Awesome.
Yeah. Now, what we want to do is put, so Shrinil said this in the pause that we had, but put Dirac Spinors, Weyl Spinors together into a Dirac Spinor. That's the idea behind a Dirac Spinor. Weyl Spinors in and of themselves can describe neutrinos in the standard model. But the fermions of the leptons,
basic,
the quarks. Sorry, go on.
Very basic question. So is this a reason why the handedness also comes in of neutrinos? Yeah, okay, cool.
Absolutely. Good point.
So the Weyl representation is for purely massless fermions.
Yes.
Or rather, fermions taken in the massless limit.
Yeah.
Right.
Yeah. Well.
Okay.
Yeah, I mean.
Wait. So
you could.
So does that mean that like in order to have mass, or like construct any massive fermion, we have to mix in left and right-handed states.
You have to mix in left and right-handed. Yeah, because that's what mass does. So you can actually just at the level of classical Dirac theory, you can work out what the solution to the equations of motion look like in terms of the Weyl Spinors. So just take the massive Dirac equation, right? Just think about it in terms of, it's just a classical field theory. And then you have some some solutions to this equation of motion. And then you can kind of track what happens at the level of the Weyl Spinors. And you'll see this so-called Zwitterbewegung. That's the name of it. But so you do a wacky transform to be able to do this. But you find that you have like this zigzag motion between the two handednesses of the Weyl Spinors.
Oh.
And the rate of these oscillations is set by the mass.
Oh, wow. Okay.
That's something you could look into. Penrose talks about it in his book, The Road to Reality. He has a nice little illustration of that.
That's nice. Okay.
Everything has returned. Yeah, so that's a fun little exercise you can do. But anyway, we can now sort of plow through to Dirac spinors. We made a lot of, we really built up our appetite for them. So first, whenever we talk about Dirac spinors, we always start by talking about the Clifford algebra. Right? We talk about the gamma matrices.
Right.
So what are the gamma matrices in terms of things we understand now? Well, they are the following.
They're built up with Pauli matrices. Right?
It's exactly 4D Pauli matrices. Remember, 4D Pauli matrices came up here. Oh, this is how they transform, and they really look like this. That's how I form my gamma matrices. And the gamma matrices satisfy the Clifford algebra.
Sorry, I have another question here.
Yeah.
When you're saying that you're constructing the gamma matrices out of the Pauli spin matrices, I'm assuming this is for a specific representation, right? Like if you take the Clifford algebra in general, you could find other representations, right?
Yeah.
You're right. Yeah. So these are just a representation of the gamma matrices that will allow us to connect what we've done so far with the Dirac spinors that are about to appear. In other words, they are the representation of the gamma matrices that can act on Dirac spinors.
Okay.
Right. Sorry, I just lost them, but just seems to be very taxing for some reason to keep track of all of these screenshots. Oh, no, that's also the wrong image. Okay. So let's just start the other way around. Let's start with the Clifford algebra. Right, this is what the Clifford algebra looks like. So curly braces are anti-commutators. So I mean gamma nu plus gamma nu. And they will anti-commute to give you the metric times the identity on spinor space. Right. So you have space-time and spinor indices. So I mean, there's another way to think about it. Like when you write down fermions in the standard model, they don't have any Lorentz indices. You usually don't write them down with any Lorentz indices.
Yeah.
But they have spinor indices. Right?
Yeah.
I mean, they're composed of objects that have spinor indices. You know, the Weyl spinors inside the the Dirac spinors. So if you split it up into Weyl spinors, it look like you have spinor indices. By themselves, they don't. Now, what happens is that so-called Rarita-Schwinger equation. So if I have a spin 3/2 particle, then the spinor will have a space-time index also.
Oh, okay.
Could you please say that again?
So if I have a spin 3/2 object, like I do in supergravity, right? So if I have a gravitino, then that object will have both spinor and, well, it'll be composed of things that have spinor indices, but it'll also have a space-time index.
Okay, so a weird question. What kind of an object is that? Like, that is not a spinor, neither is that a vector.
No, it's both. I mean, at the end of the day, you could say it's just a spinor. Like, I could use my sigma and then write everything in terms of spinor indices, right?
Okay.
I kind of forget.
Yeah.
But it's an object that you could think of as dwelling on a so-called superspace. It's just one way to think about it. You don't have to, but yeah, it's an object. So that's what the gravitino would be.
Right.
Were it out there. So these are your 4 gamma matrices, but then there's a so-called gamma 5. And gamma 5 will become our friend soon.
Okay.
So in this representation, this is what it looks like. Where I is just the spinor identity.
Right.
And its eigenvalues are plus or minus 1. Just like if I had pure matrix at minus 1, 0, 0, 1. Right? Right? And that's the chirality. So you could think of chirality as coming from the gamma 5 eigenvalue.
Okay.
We can literally write down chiral projectors in terms of gamma 5. Let's look at that. So we'll come back to this expression because I still haven't introduced Dirac spinors, which is what these objects actually act on. Right?
Act on, yeah.
So, but this is what the implication is. So it's a left-handed and right-handed projector. Right, left-handed. So gamma phi gives me an eigenvalue of 1. Then it does nothing to a left-handed vector. If it's right-handed, gamma phi gives. Sorry.
The other way.
Yeah. It goes the other way around, essentially. Sorry. So if it's left-handed, then gamma phi would give me an eigenvalue of -1, and then it'll act like identity. If it's right-handed, it'll just annihilate it, and vice versa.
Right.
But what?
Right.
So first, okay, we can also write down the generators of the. Sorry about that.
Yeah, no problem.
Yeah. And then we're ready to define a Dirac spinor. So let's do Dirac spinor. As Sharon said. So I have left-handed, and then I have right-handed contravariant. So that's the important thing about Dirac.
Oh. Okay.
And the action of gamma 5 looks like this. The
Weyl Spinor components
will appear anytime, I hope. No, it won't appear. Sorry.
Okay.
So what does this mean for our chirality? It means that you either pick up the top piece or the bottom piece under the action of the projectors.
Right.
Yeah? Okay, well, I lost gamma 5. I'll just add it up, add it again. Well, okay, you could work it out from what we have above, but this is what.
Yeah, that's fine.
So now you can also take conjugation. You can also take conjugates of the Dirac spinor, and you'll notice that in the Dirac action, if you ever looked at it. And
yeah,
that is given by the following. So gamma 0, in addition to Hermitian conjugation, tells you what it means to take just the ordinary complex conjugate. That's what I mean by. Okay, let's not call it ordinary complex conjugate. Really, this is what we mean, right? So I take the Hermitian conjugate and I multiply it by gamma 0. It's not just Hermitian conjugate. That's the important thing.
Okay.
And then we can also define charge conjugation. So see, we have parity, we have charge conjugation also. Given by the following matrix. And its action on the Dirac spinors. Well, okay, so we could guess what it is, right? What could it do? Right. Well, epsilon's lower in Ray's indices, right? So
yeah,
it'll lower one index, raise another index.
Right.
Now you could say, oh, you have two different Weyl spinors here, right? What if you made it the same spinors? So instead of having psi and chi bar, what if I just had psi and psi? Then I'd have this self-conjugate object called the Majorana spinor.
Okay.
Where they are in the world, who knows? But they have a nice relationship to Dirac spinors.
Oh, weren't neutrinos at a point of time theorized to be Majorana spinors?
Yeah, they were.
And again, is that again a consequence of things being massless that we can write it this way?
Yeah, except there's neutrino masses. Yeah, you're right. As in, you could take these. It's just a kind of rotation field space you could do, right? You could just write down everything in terms of Weyl spinors, and then see like can you repackage that action in terms of Dirac spinors, something like a Dirac spinor. But you would think, oh no, it's not going to be a Dirac spinor. It's going to be a Majorana spinor. But okay, you're going to have neutrino masses, then the story is very different.
So I guess to use a really, well, this perhaps won't be a good analogy, but it's like Weyl spinors kind of form like the components of every single higher spinor we want to build up.
Absolutely. So Weyl spinors can actually be used to construct all higher spin massless field equations.
Oh, wow.
So you just take those tensor products and then you find, okay, so let's see if I can get a nice reference for that. This is what motivates, one of the motivations of twistor theory, that you want to be able to do that. So yeah, for helicity n over 2, you find, well, actually, let me, I'll drop it here for a second.
Yeah.
But then I should put this in context. It doesn't have much to do with Majorana spinors. So higher spin equations of motion. Free higher spin equations of motion. So this is what it looks like. So you just have these quantities that you could get from. I mean, they're not themselves just a product of Weyl spinors, but you know they come from essentially an irreducible piece of taking that product. You know, all left or all right.
Right.
So then Penrose's idea was to define what's called a Penrose transform to essentially solve these equations. And you obtain a so-called, so you obtain Twistor representation by doing that. Yeah, that's the game in Twistor theory.
I see. Okay.
So now we can move on to understanding, hopefully at some point, maybe not today, but eventually,
Yeah.
Twistors in DS.
Yes. Right.
Oh, sorry. DS4. There's a similar story in ADS, but the point of doing all of this is that you get twistors from the SO41 Clifford algebra. So remember we had this discussion that DS4 is a hyperboloid in a one higher dimensional Minkowski space.
Right.
And the restricted so here you had Poincaré transformations. So on flat space you have translations and rotations, right? So remember we have these rotations, Lorentz. I'm calling them rotations, but they're really Lorentz transformations and translations. But on a hyperboloid, you would just have the Lorentz transformations.
Right.
So that hyperboloid in Minkowski space in 4 dimensions would be DS3. So for DS4, you have to go to 5 dimensions, which means that your symmetry group is SO41.
Right. Yeah.
So you see, you basically have the Weyl Spinor. So normally what you would think of on flat space is that twistors are Weyl Spinors of the conformal group, which is SO42. And in flat space, you have to deal with this SO42, which is a pretty big group, right? But what happens is that you then you kind of reduce it to the Poincaré group by introducing something called an infinity twistor, whatever that means.
Okay.
In de Sitter space, though, you have a simpler choice of this infinity twistor that reduces it down to SO41 as the de Sitter group. So in many ways, the twistor space is just a space of Dirac spinors. Okay, so let's write this down. So twistor space in DS4 is, let's give it a name. Twistor space, I'll call it cool T, is just Dirac spinors of the de Sitter group.
Right.
Or let's just put it another way. Of SO41. Oh, I don't know why that's not rendering, but yeah. So basically what you do is you want now gamma matrices for SO41.
Yeah.
Right?
Yeah.
So so to get from 3 to 4, okay, even just these poly matrices, we added identity, we did some stuff. Now it's, you take your old gamma 5 and then you package it into this. So what are these taus? Okay, so you see this tau k is just I times your old school poly matrices.
Oh, okay.
Okay. Right, so it's just I times your normal. And then so taus actually satisfies some kind of quaternionic algebra. Right, but this is your now enlarged set of gamma matrices.
Ga-
And notice
gamma
that this is just
matrices, yeah.
gamma 5 of your 4-dimensional gamma matrices.
Right. Right.
So
Hmm.
now we're interested in, say, generators. Generators are given by what? They're given by gamma mu. Oh, sorry, there was no second bracket here, right? So this means that I'm taking the antisymmetric product with the mu indices.
Right.
So I'll get the following. I mean, they're all made from transformations we understand pretty simply. Okay.
Okay.
In other words,
yeah.
SO41 is generated by gamma mu over 2. Those are like the generators of the group.
Right.
So
Yeah.
this is
Okay.
slightly weird conventions, but anyway, you can kind of break it all down, you know. So okay, so you know, there's some simple identities Yesha will tell us that you can use to decompose those transformations. To make this more explicit, you want to be able to take these Twistor matrices MAB and then write them in terms of space-time indices.
Okay. Right.
Okay, so that just means that your 4 plus 1D M has a vector, bivector, and a scalar piece. It's just a decomposition if you want to make it.
Right.
Now let's talk about this infinity twistor. So this group of transformations leaves some structure invariant, right? So remember we were talking.
Your mic. Yeah.
Yeah. So SL2C transformations leave epsilon invariant.
Yeah.
Right. So here we'll have something called the infinity twistor, which is again formed from things we understand pretty well. Okay. So let me. Oh, it hung. So the infinity twistor is left invariant by SO41 transformations. And it's given by the following.
So
now what's the fun of having such an object? Remember what happened with epsilon. We can use it to raise and lower indices.
Raise and lower, yeah.
Right. So this is basically raising and lowering the indices, but of what? You could ask.
Yeah.
Of the twistors.
Twistors. Oh, okay.
Right. So the twistors are just defined on the space of Dirac Spinors.
Yeah.
And these are all structures on the space of Dirac Spinors. So, sorry, let's do that again.
Okay. So tau 2 is
I times sigma 2.
I times sigma 2. So, okay. Yeah. Oh, I see.
Okay, this is being persistently. Okay, probably won't appear because it's hung. Let me just type it out. So Z is my twistor,
Mm-hmm.
And I can also raise. So I have Z, B, I, A, B. And you also have
So,
that I, A, B. So it's kind of like a metric, you know, it'll.
right. Yeah, of course.
Now, this is what you don't have in flat space, though. Which is what makes flat space twistors complicated, is that you don't have a simple structure like this. As in, you have one, it just doesn't satisfy all the nice properties. So, but you see, it has this weird antisymmetry property. That's how it's not like a metric, but you know, on this space.
Right. Yeah.
Okay, so we're
Yeah.
back. Now the generators are traceless with respect to this quantity, right? So
Right.
remember forming these generators with products of gammas.
Right.
So yeah, these are your basic structures. Now, what do you want to do with all of this is a question, right? So
Yeah.
you sort of want to understand.
Right. Like I can see where Weyl Spinors came in, and then where Dirac Spinors came in. Now this is structure that involves Dirac Spinors. So
Yeah. So you see, you've built up to this.
right.
The harder thing for me to think about motivating is how should I say, connect to physics we're familiar with. So right now, these are just something I've defined. Right? I said that they're twistors, they're there somewhere. But what do they have to do with any fields on de Sitter space? Right? So you want to ask, what are the structures in twistor space that are associated to points in de Sitter space? You see? You want something like our sigma, basically. Or X twiddle, something like that.
Yeah, yeah. Some sort of contraction with that.
Yeah, yeah. So what you want to do is you want to define these kinds of quantities. Let's put it this way. So I'll go backwards from the conventional treatment.
Yeah.
Okay. So what is P plus and P minus, right? That's formed.
Yeah.
So you can define this in either mixed indices. Oh, sorry, I just replaced what I had before, which is not what I intended at all. Okay, but so let's just start there.
But it's fine. Yeah.
Yeah. Or you can raise these indices, and what you can form from this is the kind of connection that we had between X and sigma. Now we're doing this with de Sitter. But note that this is not necessarily just ds. This is like a complexified version of ds. That's another added twist to this whole story.
Yeah.
And let's see. So let's do that. Okay. This is hanging. Anyway, eventually this will appear.
There we go.
But you see what we're building up here, right?
Right, right, yeah.
Oh, I don't know where I went. feel like this is at its limit. But anyway, you see, this is the kind of thing that you want to do. You want to build a bridge from
Right.
the Sitter space back to what you had, right? Like back to this Twistor space.
Right.
And in particular, that's what this Penrose transform will involve. The thing that I mentioned would solve those free field equations.
Yeah. Yeah.
Field equations over here.
Right. Yeah.
So I mean, that would be a little bit more of an involved exercise as to go through all of that. We've already covered a lot today. So if you want, we could just
we built so much. Yeah.
Yeah.
Yeah. I guess
Pause.
we can pause now and keep that for episode 2 because that sounds interesting.
Yeah, we could do a lot. We could also touch on supersymmetry. There's all kinds of things.
Yeah. All right. So I will start the recording now. You will receive an email notification when the cloud recording is